Hello, everyone. In today's lesson, we're going to explore a fascinating and powerful type of sequence. We'll be looking at geometric sequences and series. Our main goal today is to become comfortable with the fundamental formula for these sequences. By the end of this first part, you will be able to find any term in a geometric sequence using the nth term formula. Let's write that down. Our objective is to use the formula for the nth term of a geometric sequence. So what makes a sequence geometric? Unlike an arithmetic sequence where we add a common difference, in a geometric sequence we multiply by a constant value to get from one term to the next. This constant multiplier is called the common ratio, which we denote with the letter r. In other words, to get any term, you multiply the previous term by this common ratio. Let's look at a few examples to make this clear. Consider the sequence 3, 6, 12, 24, 48, and so on. What are we multiplying by each time? To get from 3 to 6, we multiply by 2. From 6 to 12, we multiply by 2. From 12 to 24, again by 2. The pattern holds. So for this sequence, the common ratio is 2. Here's another one, 80, 40, 20, 10, 5. What's the common ratio here? We're dividing by 2 each time. Remember, dividing by 2 is the same as multiplying by its reciprocal. So the common ratio r is 1/2. The common ratio doesn't have to be positive. It can be negative, which creates an alternating sequence. Take a look at this. 2, -6, 18, -54, 162. To get from 2 to -6, we multiply by -3. From -6 to 18, we multiply by -3 again. Since a negative times a negative is a positive, this pattern continues. Here, the common ratio is -3. Now let's generalize this. If we call the first term u sub 1 and the common ratio r, we can build any geometric sequence. The first term is u sub 1. To get the second term, we multiply by r, so it's u sub 1 times r. For the third term, we multiply by r again, giving us u sub 1 times r squared. The fourth term is u sub 1 times r cubed, and so on. Do you see a pattern between the term number and the power of r? For the second term, r has a power of 1. For the third term, a power of 2. For the fourth term, a power of 3. The power of r is always 1 less than the term number. This gives us our key formula for the nth term. The nth term, u sub n, is equal to the first term, u sub 1, multiplied by the common ratio r, raised to the power of n minus 1. This formula is incredibly useful because it lets us find any term in the sequence without having to calculate all the terms before it. Let's apply it to an example. A geometric sequence has a first term of 3 and a common ratio of -2. We need to find the 10th term. First, let's identify our variables for the formula. The first term, u sub 1, is 3. The common ratio r is -2. And we want to find the 10th term, so n is 10. Now we substitute these values into our formula. U sub n equals u sub 1 times r to the power of n minus 1. So u sub 10 equals 3 times -2 raised to the power of 10 minus 1, which is 9. Now we just need to calculate the result. -2 to the power of 9 is -512. So we have 3 times -512, which gives us -11536. The 10th term of this sequence is -1536. So we've seen how to use the formula to find a specific term. We have successfully met our learning objective for this section. Welcome back. In the last segment, we learned how to find a term in a sequence when we knew the start. But what if we don't know the first term or the common ratio? In this scene, our objective is to find the first term, u sub 1, and the common ratio r when we are given 2 other terms in the sequence. This is like a detective problem. We have a couple of clues, and we need to work backward to find the starting point and the rule. Let's dive into an example. The second term of a geometric sequence is 6, and the fourth term is 96. We need to find the possible values for the first term and the common ratio. We'll use our fundamental formula, u sub n equals u sub 1 times r to the n minus 1, to translate this information into equations. First, let's use the information about the second term. We know u sub 2 is 6. Using the formula, this means u sub 1 times r to the power of 2 minus 1 equals 6. This simplifies to u sub 1 times r equals 6. Let's call this equation 1. Next, let's do the same for the fourth term. We know u sub 4 is 96, so u sub 1 times r to the power of 4 minus 1 equals 96. This simplifies to u sub 1 times r cubed equals 96. We'll call this equation 2. Now we have a system of two nonlinear simultaneous equations. How can we solve this? With arithmetic sequences, we often used subtraction. Here, because the terms are multiplied, division is the most effective method. We can divide equation 2 by equation 1. This will cancel out the u sub 1 term. Let's write that out. U sub 1r cubed divided by u sub 1r equals 96 divided by 6. On the left side, the u sub 1 terms cancel, and r cubed divided by r is r squared. On the right side, 96 divided by 6 is 16. This simplifies beautifully to r squared equals 16. Now we need to solve for r. What number, when squared, gives 16? Be careful. There are two possibilities. Taking the square root of both sides, we find that r can be positive 4 or negative 4. This means there are two possible geometric sequences that fit our initial clues. We're not done yet. We still need to find the first term, u sub 1, for each of these possible ratios. We can use equation 1, which was u sub 1 times r equals 6. Let's start with the case where r is 4. If r equals 4, we substitute it into equation 1. U sub 1 times 4 equals 6. Dividing by 4, we get u sub 1 equals 6 over 4, or 1.5. Now for the second case, where r is negative 4. If r equals negative 4, we do the same. U sub 1 times negative 4 equals 6. Dividing by negative 4, we get u sub 1 equals negative 1.5. So we have two possible solutions. The first possibility is a first term of 1.5 and a common ratio of 4. The second is a first term of negative 1.5 and a common ratio of negative 4. Both of these sequences will have a second term of 6 and a fourth term of 96. By setting up and solving simultaneous equations, we have successfully found the unknown first term and common ratio, meeting our objective. Hello again. We've learned how to find a specific term and how to find the sequence's parameters. Now let's tackle another common problem. Our objective for this scene is to determine the number of terms, which we call n, in a finite geometric sequence. This means we're given a sequence that has a clear beginning and end, and our job is to figure out how many steps it takes to get from the start to the finish. Let's look at an example. We need to find the number of terms in the sequence that starts with 1, 2, 4, 8, and ends with 5, 12. First, let's identify the key components of this sequence. We need the first term and the common ratio. Clearly, the first term, u sub 1, is 1. To get from one term to the next, we are multiplying by 2, so the common ratio r is 2. We also know the last term of the sequence. This is our nth term, u sub n. The last term, u sub n, is 5, 12. Our goal is to find the n that corresponds to this term. We'll use our standard formula, u sub n equals u sub 1 times r to the n minus 1, and plug in everything we know. Substituting our values, we get 512 equals 1 times 2 to the power of n minus 1. This simplifies nicely. We have the equation 512 equals 2 to the power of n minus 1. Now we need to solve for n. There are a couple of ways to do this. If you're familiar with powers of 2, you might recognize 512. If not, we can use logarithms. One way is to take the logarithm of both sides. This allows us to bring the exponent, n minus 1, down as a multiplier. We can then isolate n minus 1 by dividing log of 512 by log of 2. Using a calculator, log of 512 divided by log of 2 is 9. So n minus 1 equals 9, which means n equals 10. There are 10 terms in this sequence. Another method, especially useful with a graphing calculator, is to use the table function. You can define a function for the nth term, in this case y equals 2 to the power of x minus 1, and then look at the table of values. You would scroll down the table until you find the x value where the y value is 512. As you can see from this example table, when n is 10, the term is 512. This confirms our answer. So 512 is the 10th term in the sequence. We have now successfully used the nth term formula to find the total number of terms in a sequence, fulfilling our learning objective. So far, we've focused on individual terms in a geometric sequence. But what if we want to add them up? This is a very common and important task. In this scene, we have two objectives. First, to understand the proof for the sum of a geometric series, and second, to use the resulting formula to calculate that sum. When we add the terms of a sequence, we call it a series. The sum of the first n terms of a geometric sequence is called a geometric series, and we denote it as S sub n. So S sub n is the sum of the first n terms. There's a very elegant formula for this, but I want to show you where it comes from first. Understanding the proof is key. Let's prove the sum formula. First, let's write out S sub n in terms of u sub 1 and r. S sub n equals u sub 1 plus u sub 1 times r plus u sub 1 times r squared, all the way up to the last term, which is u sub 1 times r to the n minus 1. Now for the clever trick. Let's take this entire equation and multiply every single term by r. On the left, we get r times s sub n. On the right, u sub 1 becomes u sub 1r, u sub 1r becomes u sub 1r squared, and so on. The last term, u sub 1r to the n minus 1, becomes u sub 1r to the n. Now look at our two equations, a and b. Do you see how many terms they have in common? Almost all of them. This suggests we can get a lot of cancellation if we subtract one equation from the other. Let's subtract equation b from equation a. We have s sub n minus r, s sub n on the left. On the right, we have the first series minus the second series. Notice that the u sub 1r term cancels. The u sub 1r squared term cancels. In fact, all the middle terms cancel out. The only terms that don't cancel are the very first term from equation a, which is u sub 1, and the very last term from equation b, which is u sub 1 r to the n. So the result is u sub 1 minus u sub 1 r to the n. We're almost there. Now we just need to solve for s sub n. Let's factor both sides. On the left, we can factor out s sub n to get s sub n times 1 minus r. On the right, we can factor out u sub 1 to get u sub 1 times 1 minus r to the n. To get s sub n by itself, we need to divide by 1 minus r, and this is a crucial step. This gives us our final formula. S sub n equals u sub 1 times the quantity 1 minus r to the n, all divided by 1 minus r. Now take a moment to think. At what point in this proof did we make an assumption? It was in that last step. We can only divide by 1 minus r if it's not 0. This means the formula is only valid if the common ratio r is not equal to 1. This is a very important condition. So what happens if r does equal 1? Let's think about that sequence. It would be u sub 1, u sub 1, u sub 1, and so on. If we add n of these terms together, the sum is simply n times u sub 1. It's a much simpler case. You might also see the sum formula written in a slightly different way. If we multiply the top and bottom of our formula by -1, we get an equivalent formula. S sub n equals u sub 1 times r to the n minus 1 divided by r minus 1. This version is often handier when r is greater than 1, as it helps avoid working with negative numbers. Great. We've derived the formula and understood its conditions. We have met our first objective. Now let's move to the second and apply it. Now that we have the formula for the sum of a geometric series, let's put it into practice. Our objective is to apply this sum formula to solve problems, and we'll specifically look at how to handle sigma notation. Let's start with a direct application. A geometric sequence has a first term of 16 and a common ratio of -0.5. We need to find the sum of the first 8 terms and round our answer to 3 significant figures. First, let's list our knowns. The first term, u sub 1, is 16. The common ratio r is -0.5, and the number of terms n is 8. Since r is less than 1, the formula s sub n equals u sub 1 times 1 minus r to the n over 1 minus r is a good choice. Plugging in the values, s sub 8 equals 16 times the quantity 1 minus -0.5 to the power of 8, all divided by 1 minus -0.5. Let's simplify this step by step. The denominator, 1 minus -0.5, becomes 1.5. In the numerator, -0.5 to the power of 8 is a small positive number. Specifically, it's about 0.0039. So we have 16 times about 0.996, all divided by 1.5. Putting this into a calculator gives us the final value. The result is approximately 10.633. Rounding to 3 significant figures, we get 10.6. Now let's tackle a problem involving sigma notation. This notation is just a compact way of writing a sum. We need to evaluate the sum from r equals 2 to 8 of the expression 2 times 4 to the power of r. The first step is to understand what this sum represents. Let's write out the first few terms. The sum starts at r equals 2, so the first term is 2 times 4 squared. The next term is for r equals 3, which is 2 times 4 cubed, then 2 times 4 to the fourth, and so on, up to the last term where r is 8. This is a geometric series. To use our formula, we need to identify the first term, the common ratio, and the number of terms. This is the most important part of solving these problems. The first term of our sum, which we call u sub 1, is the value when the index r is 2. So u sub 1 is 2 times 4 squared, which is 32. The common ratio is the base of the exponent, which is what we multiply by each time. In this case, the common ratio is 4. Finally, how many terms are there? We are summing from r equals 2 to r equals 8. Be careful, it's not 8 minus 2. The number of terms is the last index minus the first index plus 1. So 8 minus 2 is 6, plus 1 gives us 7 terms. There are 7 terms in this series. Now we have all the pieces. U sub 1 is 32, r is 4, and n is 7. Since r is greater than 1, let's use the alternative formula. S sub 7 equals 32 times 4 to the 7th minus 1, all divided by 4 minus 1. The denominator is 3. 4 to the 7th is 16,384. So we have 32 times 16,383 divided by 3. This calculates to exactly 107.52. As you can see, even with just 7 terms, the sum can get very large very quickly. This is a key feature of geometric series with a ratio greater than 1. We have now successfully applied our sum formula to both a standard problem and one with sigma notation, meeting our objective. Geometric sequences can seem abstract, but their property of rapid growth has profound real-world implications. There's a famous legend that illustrates this perfectly. Our objective here is to appreciate the rapid, often counterintuitive nature of geometric growth using the classic chessboard problem. The story goes that the inventor of chess showed the game to a king who was so impressed he offered the inventor any reward. The inventor made what seemed like a humble request. He asked for 1 grain of wheat on the first square of the chessboard, 2 grains on the second, 4 on the third, and so on, doubling the amount for each of the 64 squares. The king, thinking this was a tiny price, readily agreed. Let's analyze this request using what we know about geometric sequences. This is a geometric sequence where the number of grains on each square is a term. The first term, u sub 1, is 1. The amount doubles each time, so the common ratio r is 2. There are 64 squares, so we will have 64 terms. First, let's figure out how many grains are on the very last square, the 64th square. We need to find u sub 64. Using our formula for the nth term, u sub 64 equals u sub 1 times r to the power of 64 minus 1. That's 1 times 2 to the power of 63. Now, 2 to the 63rd is an astronomically large number. It's approximately 9.22 quintillion grains. That's just on the last square alone. The king was already in trouble. But the request was for the total amount of wheat, so we need to find the sum of all the grains on all 64 squares. We need to calculate S sub 64. We'll use our sum formula. S sub n equals u sub 1 times r to the n minus 1 over r minus 1. Let's plug in our values. S sub 64 equals 1 times 2 to the 64th minus 1, divided by 2 minus 1. The denominator is just 1, so the total sum is 2 to the 64th minus 1. This number is roughly double the amount on the last square. It's approximately 18.4 quintillion grains of wheat. Our intuition struggles to grasp such a quantity, so let's put it in context. Let's say a grain of wheat has a mass of about 0.1 grams, and the total annual worldwide production of wheat is about 7.5 times 10 to the 14th grams. The total mass required for the reward would be about 1.84 times 10 to the 18th grams. Compare that to the annual world production of 7.5 times 10 to the 14th grams. How many years of the entire planet's wheat production would it take to pay the reward? We divide the total mass required by the annual production. The result is about 2,450 years. The king would have needed all the wheat grown in the entire world for nearly 2.5 millennia to fulfill his promise. This example powerfully demonstrates that geometric growth is explosive. Even starting with just 1, doubling a number of times leads to unimaginable quantities. This is a key takeaway that applies to many areas, from population growth to financial investments. We've seen the power of geometric growth. Now let's turn to one of its most common and important real-world applications, money. Specifically, we'll be looking at the financial applications of geometric sequences. Our objective for this scene is to model compound interest problems using the tools we've just developed for geometric sequences. The core idea is compound interest. Compound interest is when you earn interest not only on your initial amount of money, called the principal, but also on the accumulated interest from previous periods. It's interest on interest. This process, where a percentage increase is applied repeatedly to a growing sum, is a perfect example of a geometric sequence. The initial amount is our present value, or PV. The amount after some time is the future value, or FV. The interest rate per period creates a multiplier, our common ratio R, which is 1 plus the interest rate. A key detail is the compounding period. Interest is often quoted as an annual rate, but it might be calculated or compounded more frequently, like monthly or quarterly. If that happens, you have to adjust the rate and the number of periods. You divide the annual rate by the number of periods per year, and you multiply the number of years by that same number. Let's see this in an example. A savings account has an annual interest rate of 3%, compounded monthly. We want to find the amount in the account 18 months after $5,000 is invested. First, let's break down the problem and find our parameters. The initial investment, or present value, is $5,000. The annual interest rate is 3%, but it's compounded monthly, so we need to find the monthly interest rate. We divide the annual rate by 12. So 3% divided by 12 is 0.25% per month. This monthly rate gives us our common ratio, or multiplier. The ratio R is 1 plus the monthly rate as a decimal, so 1 plus 0.0025, which is 1.0025. This is the factor our money is multiplied by each month. Finally, the number of periods. The investment is for 18 months, and interest is compounded monthly, so the number of periods, n, is simply 18. Now we can calculate the future value. The future value is just the nth term of this financial sequence, starting from an initial value PV. The formula is future value equals present value times the common ratio to the power of n. So we have 5,000 times 1.0025 to the power of 18. Plugging this into a calculator, we get approximately $5,229.85. After 18 months, the initial $5,000 has grown by about $230. Many financial calculators have a built-in time value of money, or TVM solver, that does this automatically. You would input N, the annual interest rate I%, the present value PV, and the number of compounding periods per year, and it would solve for the future value FV. But understanding that this is just a geometric sequence allows you to solve it from first principles, which is a much more powerful skill. We have successfully modeled a compound interest problem, meeting our objective. In our final scene, we'll look at two other important financial concepts that are also modeled by geometric sequences: depreciation and inflation. Our objective is to calculate the effects of depreciation and inflation on the value of an asset or investment. Let's start with depreciation. While investments hopefully grow, many assets, like cars or electronics, lose value over time. This loss of value is called depreciation. Calculating depreciation is almost identical to calculating compound interest, but the percentage change is negative. It's a geometric decay instead of a geometric growth. So if an asset depreciates by, say, 15% per year, its value is multiplied by 1 minus 0.15, which is 0.85 each year. The common ratio R is less than 1. Now let's talk about a more subtle concept: inflation. Inflation is the rate at which the general level of prices for goods and services is rising, and subsequently, purchasing power is falling. In simple terms, a dollar today buys more than a dollar in the future. Inflation effectively depreciates the value of money itself. This leads to the idea of real value. The nominal value of your money is the number on your bank statement. The real value is what that money can actually buy after accounting for inflation. Distinguishing between nominal and real value is crucial in finance. There's a simple approximation to find the real rate of return on an investment. The percentage change in your real wealth is approximately the nominal percentage change of your investment, which we'll call C, minus the rate of inflation, I. Let's see how this works in an example. An investment account offers 2% annual interest. During the same period, there is inflation of 2.5% per year. What is the value in real terms of a £1,000 investment after 5 years? First, let's find the approximate annual real terms percentage change using our formula. The real rate is approximately the nominal rate of 2% minus the inflation rate of 2.5%, which gives us negative 0.5%. This means that even though our investment is growing in nominal terms, its actual purchasing power is decreasing. A decrease of 0.5% corresponds to a multiplier. The multiplier for our real value is 1 minus 0.005, which is 0.995. Now we can calculate the real value of the investment after 5 years. We take the initial investment of £1,000 and multiply it by our real terms multiplier, 0.995, raised to the power of 5 for the 5 years. This gives us approximately £975 and 25 pence. So after 5 years, while the bank account might show more than £1,000, the purchasing power of that money is equivalent to only about £975 today. It's worth noting that this formula, R equals C minus I, is a very good approximation for small percentages. The true method involves dividing the nominal multiplier by the inflation multiplier. The true real multiplier would be 1.02 divided by 1.025, which is about 0.99512. As you can see, it's very close to our approximation of 0.995, which is why the approximation is so useful. And with that, we've covered the key ideas of geometric sequences, from their basic definition to their powerful applications in the world of finance. You are now equipped to analyze growth, decay, and the real value of investments over time.